All right. Let's move on. We have started in the last class with the crystal field theory, and we have applied crystal field theory so far to an octahedral complex. So we said that when we have an octahedral complex, then we have an octahedral crystal field, and that crystal field leads to a repulsion between the electrons in the ligands and the electrons in the d orbitals. But the electrons are not equally repelled. So because of geometric arguments, the electrons in the dx square minus y square orbitals and the dz square orbital is repelled more in comparison to the electron, the dxy, the dyz, and the dxz. Okay, now we can apply the same arguments also to other shapes. So, for instance, we can apply the same procedure also to tetrahedral complexes that have a tetrahedral crystal field. So, in the case of the tetrahedral crystal field, the assignment of the coordinate system is a little bit less straightforward. We can make a reasonable decision about the coordinate system when we remember that we can inscribe a tetrahedron inside of a cube. So you see, what you see here is a cube with a metal in the center, and now we can occupy 4 of the 8 corners of the cube. So we occupy every other corner of the cube, and you see that when we do this, the respective ligands are occupying the corners of a tetrahedron. You can easily see that if you connected the ligands, that would build you a tetrahedron. So that helps us to define the coordinate system. It would make sense to define the coordinate system so that the axes would stand perpendicular to the faces of the cube. So we could define the x-axis pointing to the left here, standing perpendicular to this face. The y-axis pointing to the front, standing perpendicular to this face here. And the z-axis pointing upward, standing perpendicular to this face here. So of course, the definition of the coordinate system is very important because it now defines the orientation of the orbitals relative to the ligands. Okay, so now when we think about the orientation of the orbitals relative to the ligands, we can again estimate to which degree the ligand electrons should repel the electrons in the respective d orbitals. Okay, so now in the case of the dz square and the dx square minus y square orbitals, we realize that these two orbitals have their electron density primarily on the axes. Okay, we said that the dz square orbital has its electron density primarily on the z-axis. The dx square minus y square orbital has its electron density primarily on the x and the y-axis. Now we see that the ligands do not approach on these axes, and for that reason, these orbitals face now relatively small electrostatic repulsion from the ligands. So therefore, relative to a spherical crystal field, the energy of this orbital is lowered. So now it's again lowered exactly by the same amount of energy, which is not entirely obvious, given that these orbitals have very different shapes. But it helps us again to remember that these two orbitals have the same symmetry within the point group TD. Okay, so a tetrahedral belongs to the point group TD, and within the point group TD, a dz square and a dx square minus y square orbital are doubly degenerate, and they have both the symmetry type E. So again, we can apply the principle that when two orbitals are degenerate in symmetry, they also degenerate in energy, which explains why they have the same energy, despite the fact that they're having very different shapes. So now what about the remaining orbitals? So the remaining orbitals are the dxy, the dxz, and the dyz. Now those orbitals, they have their lobes in between the axes, as you can see here. So the dxz has a slope in between the x and the y axis. The xz has the lobes in between the x and the z axis, and the dyz has the slopes in between the y and the z axis. Okay, so now the ligands are approaching in between the axes, and for that reason, these three orbitals experience a comparatively high electrostatic repulsion, higher than in comparison to the spherical crystal field. So again, the increase of the energy is by exactly the same amount, and again, we can make symmetry arguments in order to explain this. Within the point group TD, our three orbitals have all the symmetry type T2, and as they are triply degenerate symmetry-wise, they also degenerate energy-wise. Okay, now again, we can define the energy difference between the E orbitals and the T2 orbitals as a delta, and we would label this delta delta T because it relates to tetrahedral crystal field. So now again, because of energy conservation arguments, the E orbitals must be 3/5 of delta T below the energy level of the orbital in the spherical crystal field, and the T2 orbitals must be increased in energy by a value of 2/5 of delta 2. Okay, so now another important consideration is that the tetrahedral field is generally weaker than the octahedral field. So the tetrahedral crystal field splitting, and that's just the delta T value, is only 4/9 in comparison to the octahedral case, delta O. All right, and that can be explained by two arguments. First of all, in the tetrahedral case, fewer ligands are available for crystal field generation. Okay, and secondly, the T2 orbitals, even though approaching in between the axes, do not point exactly toward the corners of the tetrahedron. Okay, and therefore the repulsive interactions are not as as strong as the repulsive interactions of the x square minus y square and the z square orbital in the octahedral case. So with these two arguments, you can explain why the tetrahedral crystal field splitting is actually smaller than the octahedral crystal field splitting. All right. So now let us go from the tetrahedral crystal field to a tetragonally distorted octahedral crystal field and a square planar crystal field. So we will see that these crystal fields are interrelated from each other. One can derive the crystal field of a tetragonally distorted octahedral crystal field from the octahedral crystal field, but also the square planar crystal field can then be derived from the tetragonally distorted crystal field. So how does this work? Let's start again out from the ideal octahedral crystal field. So in the ideal octahedral crystal field, we have our T2G orbitals and our EG orbitals that have an energy difference of delta O in between them. So now let us distort our octahedron and see how the energies of these orbitals should change. Okay, so we assume an elongated distortion as an example, and that moves these two ligands in Z direction further away from the metal. Okay, now we have to keep in mind that we have to keep the overall crystal field strength the same as compared to the non-distorted case. Otherwise, we are starting to compare apples and oranges. And therefore, in order to compensate the loss of crystal field due to the fact that we move away these two ligands from the metal center, we have to move the other four ligands slightly toward the metal, okay? Creating somewhat stronger interactions, which are compensating the weakened interaction. So this just keeps the overall crystal field to be the same. Okay, now let us think about how the energies of the orbitals should change, and we can just go through the orbitals one by one. So we can, for instance, start with the dz square orbital. So the dz square orbital points into Z direction. So as we move away the ligands in Z direction, well, the electrostatic repulsion should decline, and therefore the energy of our dz square orbital should also decrease. So now next, we can look at the dx square minus y square orbital. So can someone tell me what should happen to the energy of this orbital? I think it's pretty straightforward to predict.
Is like the whole thing gonna shift down, or is it gonna?
Sorry?
Is it just the whole thing, like the energy separation of the whole thing going to shift down, or is it going to decrease?
Yeah, right at the moment, we are only looking at the dx square minus y square orbital individually.
Okay.
Yeah. So in the first step, we say that the dc square moves down in energy. So now, what will happen to the dx square minus y square? It will move up in energy for the reason that these four ligands here, they are moving closer to the metal. Okay. So now let us look at the remaining orbitals. So we have the dxy, the dyz, and the dxz. So now the dxy lies also in the xy plane, where the ligands are now closer to the metal. And for that reason, the dxy moves up in energy. The other two, because they have a strong z component, they move down in energy and move down in energy by the same amount. Okay. Now we can think about how we would fill the electrons into our orbitals, and doing so, try to predict under which conditions such tetragonal distortion should take place. one of the nice things about crystal field theory is that it can actually explain these distortions by pretty simple arguments. So here in this example, as you can see for the ideal octahedron, we have assumed a D9 electron configuration. Okay, the metal in the center could be, for instance, a copper 2 plus ion. It's octahedral coordinate. So in the octahedral crystal field, we would therefore have 6 electrons here into the T2G orbitals, and we would have 3 electrons in the EG orbitals. Now it is known for copper 2 octahedral copper 2 plus complexes that they like to tetrahedrally distort. So, sorry, tetragonally distort. So can we explain this? Now, how would we need to fill the electrons in? Well, we would need to fill the first 4 electrons into the dxy, so the dxz and the dyz. So this electron here, these two would go into the dyz. These two here now would go into the dz square, and the last one would need to go into the dx square minus y square. Okay, so now we can see that we actually have a net stabilization of electron energy due to the distortion. Because previously we had these 3 electrons having the same energy, so they were degenerate. Now by the distortion, we can decrease the energy of 2 electrons, and it's the 2 electrons that are in the dz square orbital, and we only need to increase the energy of 1 electron. So overall, the energy of these 3 electrons has been lowered. And that can now, of course, explain why this tetragonal distortion happens. The octahedral complex can lower its energy by tetragonally distorting. Okay, now this also helps us to predict for which other electron configurations an octahedral complex may distort. So for instance, if we removed another electron, we would actually remove our electron here in the dx square minus y square orbital, and then we would not need to destabilize any electron, okay? And we would have even a greater driving force for the tetragonal distortion. So in this case, we would have a D8 electron configuration. Now remember, the D8 electron configuration likes the square planar shape. Okay? And now we can say that, well, a square planar shape is nothing else but an extreme case of a tetragonally distorted octahedron. So if I move my 2 ligands along the z-axis infinitely far away from the metal, okay, then I have made my transition from a tetragonally distorted octahedron basically to a square planar complex. You can say a square planar complex is nothing else but an extreme case of a tetragonally distorted complex. So now, in the case of a square planar complex, how would our orbitals move in energy starting out from the tetragonally distorted complex, where the energy of the dz square orbital, should further decrease, and the energy of the dx square minus y square orbital should further increase. Okay, so here the energy of the dx square minus y square orbital has further increased, so the energy of the dz square orbital has significantly decreased. So what about the other orbitals? So now the dxy should go further up in energy, and because it goes further up and the dz square orbital goes further down, the energy of the dxy is now above the energy of the dz squared. Okay, so they switch up their places, relative places. So further, the dxz and the dyz go further down in energy. Okay, so now I need to fill in my 8 electrons, and you can see that I can further stabilize my electron energy overall. So certainly the energy of the electron in dz square orbitals has been further stabilized. The energy of the dxy electrons has somewhat gone up, but on the other hand, the electrons in the dxy and the dyz orbital goes further down. Okay, so I gain a lot of energy by distorting further from the tetragonally distorted octahedral field to the square planar field, and we have a nice explanation for why the D8 electron configuration actually likes the square planar shape. Okay, and now you see that the crystal field theory, even though not a bonding theory in itself, because it's based on electrostatic interactions, can nonetheless make statements that are typical for bonding theory. For example, the explanation of a shape. Okay, we can also now this way explain why, well, we have 4 bonds and why we have a square planar shape. Okay, so now crystal field theory cannot only explain shapes nicely, it can also explain the magnetism of complexes very nicely, including high spin and low spin complexes. And remember, the valence bond theory had enormous difficulties with these kind of complexes. You will see that the crystal field theory can nicely explain this phenomenon. Okay, so how does this work? Well, crystal field theory just says that, well, different ligands produce differently strong crystal fields, and depending on the strength of the crystal field, we have either a low spin complex or a high spin complex. If the crystal field is strong, then we have a low spin complex, and when the crystal field is weak, we have a high spin complex. So for instance, so generally, when we have a large crystal field, then the spin pairing energy is being overcome, and we pair the electrons. If that crystal field is not strong enough, we will remain to have high spin complexes. So for instance, here in the D4 electron configuration, and assuming an octahedral complex, we would have 3 T2G orbitals and 2 EG orbitals. So we would have 4 electrons available. And if that energy difference between the TG orbital and the EG orbital is assumed to be smaller than the spin pairing energy, then we would assume that all the electrons would want to go with spin up into these orbitals, obeying the Wund's rule. So we would say that, well, we would observe a small energy difference between the T2G and the EG orbital. In the case, we have a weak ligand field. Okay, whereas when we have a strong field ligand, this energy difference is significantly larger, and then the spin pairing energy is being overcome. So our 4th electron moves from the EG orbital into the T2G orbital. Okay? So now we can apply the same principle also to other electron configurations. So for instance, when we have a D5 electron configuration, and we have a ligand that only produces a weak crystal field, then we would fill the electrons into the orbital according to Hund's rule, and that would give us 5 unpaired electrons. So if we had strong ligand field, then these 2 electrons in the EG orbitals would go down into the T2G orbitals because the spin pairing energy is overcome, and that would reduce the number of unpaired electrons from 5 to 2. From 5 to 1. Okay, the same we can also do for the d6 electron configuration. So the d6 electron configuration, you necessarily must pair one of the electrons that has a spin up, so that leaves us 4 electrons with unpaired spins. But if we increase the size of the crystal field, we can move these 2 electrons here into the EG orbitals, so T2G orbitals, and then you see that all the electrons are being paired, and we have a diamagnetic complex. So for the d7 electron configuration, we have an additional electron, so we must pair 2 electrons in the T2G orbitals. So that leaves us 1, 2, 3 electrons that are unpaired. If we increase the crystal field, the electrons would like to move down, but you see that in this case, only 1 electron can move from the EG orbital into the T2G orbital, because after that movement, our T2G orbitals are completely full, and that means that our second unpaired electron must remain in the EG orbital. Okay, now with this picture in hand, we can also understand why there are no high and low spin complexes for the electron configurations D1 to D3, and for the electron configurations D9 and D10. So for instance, when you have an electron configuration of D3, okay, all the electrons, the 3 electrons, can be filled to spin up into the T2G orbitals. Okay, therefore there are no electrons, and the spin multiplicity is already maximized. And therefore, no electron would be available for spin pairing because the EG orbitals are being empty. So for the D9 electron configuration, on the other hand, our T2G orbitals would be already full to begin with. So any electrons that are in the EG orbitals couldn't be moved down into the T2G orbitals because they're already full. Okay, of course, for the D10 electron configuration, the same would be true. All right. So the crystal field theory also nicely explains why high and low spin complexes are found in octahedral complexes, but not in tetrahedral complexes, because it can predict that a tetrahedral crystal field is inherently weaker than an octahedral crystal field. That is just 4/9 of an octahedral crystal field. So no matter what ligands we use, these ligands never produce a crystal field which is large enough to overcome the spin pairing energy. Okay, now from that you can see that our crystal field theory, with basically just very few assumptions, can nicely explain magnetism in complexes, but it cannot only explain magnetism, it can also explain optical properties. So many coordination compounds have color, and color arises from electron transitions, and because we now have d orbitals of different energies available, we can explain electron transitions, which can explain color, and we can develop what is called a spectrochemical series that basically links the properties of ligands to the color of a compound. So generally, the smaller the wavelength of the absorption, the stronger the crystal field of the ligand is. So for instance, when we have a hexa-aquachromium 2+ complex, then we have an octahedral complex that has T2G orbitals and EG orbitals, and we have a chromium 2+ ion in this case, so we have a D4 ion, so we have 4 d electrons available. So now the aqua ligands do not produce a very strong crystal field. Okay, so for that reason, we have a high spin complex here, as you can see. And because we have a relatively small delta O, we do not need a lot of energy to promote an electron from the T2G orbital into an EG orbital. So therefore, light of relatively large wavelength is enough in order to excite our electron from a T2G orbital and EG orbital. Whereas, for instance, when we have a chromium, hexacyanochromium 4- complex, we have a low spin complex because we have significantly larger delta O, but it now requires more energy in order to promote an electron from a T2G orbital into an EG orbital. So therefore, we would require electromagnetic radiation with shorter wavelengths. Okay, so overall, this electron transition here requires only longer wavelengths, and this transition here requires shorter wavelengths. Okay, so now what you can do is you can make chromium complexes, octahedral chromium complexes with all kinds of different ligands, and just compare the absorption spectra of the respective complexes, which then gives you information of your delta O. And you can order the different ligands relative to each other, okay? From longer wavelengths to smaller wavelengths, corresponding to a smaller delta O to a larger delta O. And this is what is called a spectrochemical series. So here we have a few ligands, of course there are many more ligands possible, that are arranged in to a spectrochemical series. So for instance, you see here that an iodoligand produces the weakest field. It should therefore, a complex with the iodoligand should therefore absorb the light of the longest wavelength. You see, for instance, a thiocyanate ligand is approximately in the middle, and a cyanoligand, and even more so a carbonyl ligand, is very much to the right side. So these ligands require the smallest wavelength, light with the highest energy, in order to overcome the delta O and promote an electron from a T2G into an EG orbital. Okay? So you see here again that the crystal field theory, while not being a bonding theory at all, because based on electrostatic interactions, can explain phenomena typical bonding theory is supposed to explain. So what crystal field theory still cannot explain is, for instance, why certain ligands produce a strong field while other ligands produce a weak field. We cannot make arguments to explain this. And in order to explain that, we now need to go to the last bonding theory, which is the ligand field theory. Okay. All right. Then let us do this. So the ligand field theory is nothing else but molecular orbital theory applied to coordination compounds. The most powerful theory, it can make the best explanation, the best predictions, but on the other hand, it's also the most complicated theory. Okay, so it can overcome the shortcomings of the valence bond and the crystal field theory. So it can explain covalent bonding in coordination compounds. So it can explain the shapes of the coordination compounds well. It can explain the magnetism in the electronic spectra as well. In addition to that, it can also explain the stability. For instance, it can explain why the 18 electron rule often holds, yeah? But it can also explain exceptions from the 18 electron rule. Okay, disadvantage, like I said before, it is more complicated than the other theories. So what we'll basically do now is applying your knowledge that you previously have obtained in the chapter about the molecular orbital theory to coordination compounds. All right, so previously you learned to construct molecular orbital diagrams using the symmetry adapted linear combination of atomic orbitals method. And remember the rules that you need to apply in order to execute that method correctly. So the same rules apply now again, but there are some modifications to these rules to optimize that Sark process for coordination compounds. Okay, so what are our rules? The first rule is again that you have to determine the point group of the complex and assign the axes, the coordinate system, in a meaningful way. So the second rule is that you determine the relevant metal frontier orbitals for bonding. So when you have a transition metal of the fourth period, for example, that would be the 4s, the 4p, and the 3d orbitals. So after that, you look at the symmetry types of these metal orbitals, and you can do this simply by looking into the chemical table. Okay. Fourthly, you can now select the highest occupied molecular orbital suitable for sigma bonding if the ligand is a molecule. If it's only a simple ion, then select the highest occupied atomic orbital suitable for sigma bonding. This, of course, requires that you know what is the highest occupied molecular orbital of your ligand is. So therefore, you may need to first construct the molecular orbital diagram of your ligand before you can actually construct the molecular orbital diagram of your complex. Okay, so then you form ligand group orbitals from the selected ligand orbitals and determine the symmetry types. And then you combine the metal orbitals and the ligand group orbitals of the same symmetries to form molecular orbitals. So now, however, we have only formed the molecular orbitals relevant for sigma bonding, because we have selected the homos suitable for sigma bonding. So the next step, you now need to look again into your molecular orbital diagram of the ligand and see if there are also molecular orbitals suitable for pi bonding with the metal. So if that is so, you again determine the symmetry types and combine them with metal frontier orbitals of the same symmetry type. So after that, you can even go back again and see if there are more molecular orbitals suitable for delta bonding. If so, you again determine the symmetry types and then make delta bonds with the metal complex. So let us apply these rules step by step. Let us first consider an octahedral complex of a fourth period transition metal. So of course we will be in the point group OH, and the axes are easy to determine. They just point into the direction of the ligands. So the next thing you have to be clear about is what are your metal frontier orbitals. Okay, and in order to determine this, you only need to look into the character table of the point group, in this case OH. So now your 4s orbital will be a frontier orbital. Remember, 4s orbitals have always the totally symmetric symmetry type, which is always the first symmetry type in the character table. So in this case, the symmetry type is A1G. So next, you look at the 4p orbitals, which are also frontier orbitals. And then also finally the d orbital. So we already said that for s orbital is the symmetry type of A1G. So what about the p orbitals? You see, when you look into the character table, that the p orbitals are triply degenerate because the letters x, y, and z are here together in parentheses. So that indicates a triple degeneration. And we can easily determine the symmetry type by just going here to the left. Okay, and the symmetry type will be T1U. Okay, so this is the second symmetry type. So lastly, we need to look at the 3D orbitals. Now we can, for instance, start with the dxy, the dxz, the dyz. You see them here in parentheses, so that means that also these here are triply degenerate. So which symmetry type will they have? Well, just go to the left. Then you see that they have T2G symmetry. And last but not least, we have to consider the 3D z square and the 3D x square minus y square. And you see them actually both here together. So the 3D z square you see in the form of this formula here, 2z square minus x square minus y square. Remember, that is the mathematical form of a cone. And remember that 3d x square minus y square has conical nodes. Therefore, our 3d z square orbital is hidden actually behind this mathematical expression. And we see here the mathematical form for the dx square minus y square orbital. So that means that these two orbitals are also double degenerate, and the exact symmetry type you can read, let's go to the left side, which is ET. So now we have determined all the symmetry types of our metal. So the next step, we need to look at our ligand. Now, of course, it depends what ligand you have. Yeah. We're making here the assumption that we have a carbonyl ligand, the CO molecule is the ligand. Our job would be to determine the highest occupied molecular orbital in that ligand, which is suitable for signal bonding. So in order to do that, first we need to know what is the molecular orbital diagram of CO. So the CO ligand is a linear ligand. So it belongs actually to the point group C infinite V. So now the character table of this point group is more complicated because of the principal axis of the infinite order and the infinite number of vertical mirror planes. But you can simplify your considerations by reducing the symmetry to the symmetry C4V. So we reduce the order of your infinite axis from infinite to 4. This is because the order of 4 is still high enough so that you do not overlook degeneracies in orbitals. Okay, this is because while our molecule is actually a cylinder, yeah, we can well, modify this view, saying that, well, our CO molecule is an entity that has orbitals with well-defined shapes. And if we take the shapes of the orbitals themselves into account and we make them part of the entire molecule, our symmetry actually can be reduced from C infinite V to C4V. Okay, because there's no orbital that requires actually an axis of higher than 4. Okay, I'm explaining this shortly in a little bit more detail. So this is the character table of C4V, and we see that a Z orbital has the symmetry type A1. We see that Px and Py orbitals, they have the symmetry type of E. So our NES orbital would also have the symmetry type A1. So of course our valence orbitals of the CO ligand would only be the 2s and the 2p orbitals, and therefore these are the only orbitals we need to construct our molecular orbit diagram. Okay? So now we can assume that, well, our bond axis, the z-axis, okay, then our px and our py orbitals stand perpendicular to that. Therefore, actually, a 4-fold axis is enough in order to interconvert them. All right, we do not need an axis higher than that. But we should not use also a principal axis lower than that, because a principal axis lower than that could not interconvert these orbitals anymore. And that would actually lead to the fact that we would overlook the degeneracy of our x and y orbitals. So if we, let's say, went to C2V, yeah, then in the point of C2V, there would be no symmetry types that are doubly degenerate. And we would overlook that degeneracy of these orbitals, which is not desirable when you construct a molecular orbit diagram. Yeah? Because a degeneracy in symmetry always assumes a degeneracy in imaging as well. All right. So we can construct our MO fairly easily. So here you have the S and the P orbitals of oxygen. Here you have the S and the P orbitals of the carbon. So the oxygen is more electronegative than the carbon. Therefore, you have to plot the energies of the oxygen orbitals lower in comparison to the energies of the carbon orbitals. All right, you can assign symmetry types. Yeah, and now you can construct your molecular orbitals. You see that you have 2 A1 orbitals on this side and 2 A1 orbitals on the other side. So that gives you overall 4 molecular orbitals. One is, you can assume to be bonding, one interbonding, one weakly bonding, and one weakly interbonding. And you can connect them accordingly. So this would be the 1A1, 2A1, 3A1, 4A1. And then you still need to connect the E orbitals. So you have 2 here and 2 here. So that should give, well, a bonding pair and an interbonding pair. So this would be the 1E. This one here would be 2E. You would also connect them. So last but not least, you would fill in the electrons. Well, you would have 4 electrons here on the carbon side, and you would have 6 electrons here on the oxygen side. That gives overall 10. And that would fill this 1A1, this 2A1, these 1E orbitals, and last but not least, this 3A1 orbital. You see that this 3A1 orbital is now your highest occupied molecular orbital that it can use for sigma bonding. All right, then let's stop at this point and we can continue